Previously on separation and mass transfer operations, I reviewed how to solve a flash distillation problem in the way that you would have in material and energy balances. The example problem from last time involved benzene toluene at a given feed flow rate and composition, and we were also told what the temperature and pressure of the single-stage distillation unit was. And the problem asked us to solve for the molar flow rates of the vapor and liquid outgoing streams and also the compositions. We did so by deriving a list of 4 equations. So we had 2 material balances, 2 phase equilibrium relationships, which we solved for algebraically. As I hopefully demonstrated, this process was doable, but it was kind of annoying to have to go through and solve this problem for different conditions. So if I wanted to, for instance, change the temperature, I would have to go through and recalculate all this stuff. And while it wasn't difficult, it was still somewhat time consuming. Today, I'll show you a faster way to do this if you have access to a TXY or a PXY diagram. So our system is benzene toluene, and we're fortunate in that we happen to have TXY and PXY diagrams readily available. And our conditions of the flash separator are 100 C and 1 atmosphere. So I happen to have access to the TXY diagram at 1 atmosphere and also the PXY diagram at 100 degrees C. So I can use either one of these to develop my solution. And what the TXY and PXY diagrams can do for you is very quickly solve for the compositions of the 2 exiting streams. So instead of solving the 2 Raoult's laws simultaneously for XA and YA, instead what I can do is just go to my diagram and label where my process conditions are, and then that will tell me what my equilibrium compositions are. So you should get the same thing on the TXY diagram. My temperature is 100. So I just have to draw points there and there. This is where my tie line is. And I draw little dashed lines straight down so I can read the plot. And this is the disadvantage of doing it graphically, is you oftentimes lose the precision that you would have with your calculator. I'm going to call that 0.26 and 0.46. Doing it the TXY way. And doing it the PXY way, so my temperature is 100 C for this particular PXY diagram. 1 atmosphere is 760 mmHg. So once again, I've got a little bit of uncertainty here, but if I draw my tie line all the way across, I would obtain roughly the same thing. So 0.26 and 0.46. And if I check that against what I got the algebraic way, 0.456 rounds to 0.46, 0.257 rounds to 2.6. So once again, instead of solving the 2 Raoult's laws algebraically, the TXY-PXY diagram takes care of that for you automatically, because that's what these lines are, just solving these Raoult's laws over and over again. Now if I have what the compositions, XA and YA, are by looking at the graph, then it becomes a simpler exercise to solve 2 equations, 2 unknowns. So what I mean there is I would, instead of solving these algebraically, you would solve these graphically by looking at the TXY diagram, by looking up process conditions on a TXY or PXY diagram. And that would depend on whichever one you happen to have access to. So another variant of this problem would be if I only gave you pressure, say, and I asked you to find the temperature at which the composition was something else, then you would have to use a TXY diagram because you'd have to be varying temperature to find. But for this particular problem, either or would do. I'll note here that if the problem, for example, asked me for 150 C in 1 atmosphere, and these were the only 2 diagrams I have, I would have to use the PXY diagram because the pressure is 1 atmosphere and I could just change the temperature. 150 C was a bad example because that's not at equilibrium. But hopefully you see my point that if you need a condition for which you don't have the PXY or TXY diagram for, you cannot use it. And then once you have XA and YA, then you just simply plug it into the A material balance and you'd solve this system of 2 equations for now 2 unknowns, which would be your molar flow rates of the vapor and liquid phases. So you can't solve the entire problem this way, unfortunately, but it is a lot simpler to do than doing the entire thing algebraically. In the very next video, I'll show you how to solve the entire problem graphically. There is a way that you could do the whole thing graphically, but before I do that, I have to introduce the concept of relative volatility. So relative volatility is a single parameter, we'll called alpha, that describes phase equilibrium between two components. And this is very beneficial because describing phase equilibrium with a single parameter instead of two equations, which are the Raoult's laws, are going to be very, very useful in simplifying the number of equations that we have to solve. And it's going to allow us to solve flash distillation problems completely graphically. So first we have to define two more parameters. It's really just one parameter, but for each of the two components called the Ks. So Ka is going to mean our equilibrium constant for component A, and Kb is the same thing, equilibrium constant for component B. And the way equilibrium constants are defined is going to be the vapor phase composition Ya divided by the liquid phase composition Xa. Same thing for Kb, but it's the vapor phase composition of B, which is 1 minus Ya, and 1 over Xa. So by Raoult's law, you could also say that these equilibrium constants are equal to gamma A P star A divided by total system pressure, and equilibrium constant of component B is gamma B PB star over P. Alpha, then, the relative volatility, is the ratio of these two equilibrium constants, Ka divided by Kb, or alternatively, Ya over Xa over 1 minus Ya over 1 minus Xa. Just a quick note about alpha is that it must be greater than 1. So by convention, we assign A to be the more volatile component. So by convention, because A is the more volatile one, Ya, remember that is the composition in the vapor phase, is going to be greater than Xa. And by extension then, Yb, which is the mole fraction of B, the less volatile component, is going to be less than the mole fraction of the less volatile component in the liquid phase. So because if each of these two things are true, if I look at my definition for alpha now in green on the left, alpha has to be greater than or less than 1. 1 is the absolute minimum that alpha could be. This equation that I just wrote could be rearranged to solve for Ya. So go ahead and try and pause the video now and see if you can do this yourself. Solve this equation for Ya. See if you can do that. And I'll show you the steps after the pause. All right, so the first step, I'm going to undo this fraction of a fraction over a fraction and say instead alpha. And another way you might see this notated is alpha AB or alpha, whatever the two components are. So alpha for benzene toluene may be denoted as A sub BT, for example, is equal to Ya over Xa times, now because I've got a fraction over a fraction, I'm going to flip the bottom fraction to bring it up to the top. 1 minus Xa and 1 minus Ya. And then because I'm multiplying these, I'm just going to go ahead and distribute the two, or multiply the two fractions together to make it a little bit less complicated. So I've got Ya minus Xa over Xa minus Xa. Now I'm going to multiply both sides by the denominator to make it so that there's no fractions. And I'll distribute through the alpha. So I've got alpha AB times Xa minus alpha AB times all this other stuff. So minus alpha AB Xa is equal to Ya minus Xa Ya. And remember that the goal of this exercise is to solve for Ya. So I want to group everything with a Ya over onto one side. So I'm just going to add this term over here to both sides to bring it over. And because I want to solve for Ya, I'm just going to flip the equation as well. So I'm going to start with the right-hand side. So I've got Ya minus Xa Ya plus alpha AB Xa Ya is equal to alpha AB Xa. And now, because I have a common Ya, I can factor that out of this expression on the left-hand side. And I can also factor out an Xa2 from the two terms on the right. So I'm going to have Ya, and then in brackets, 1 minus and then an XA with a parenthesis, YA plus alpha AB YA. Whoops, no, I messed that up. I factored out the YA, so there are no YAs. This is just a 1 plus alpha AB now. Yep, that should be okay, is equal to alpha AB XA. Now the final step to solve for YA is to just bring this entire thing that is in the brackets over to the other side, such that I can solve for YA, and I find that YA is equal to alpha AB times XA, all divided by 1 minus alpha AB plus 1. Actually, I'm going to change it to make it plus and a minus. This is how it's oftentimes written. So this is just by, I should not have taken out the negative, right? So I could equivalently have said this, 1 plus XA minus 1. There should have been how it goes, times XA. And this is my expression, y as a function of x with the single parameter alpha. So the power of this equation is that if I knew what the value alpha AB was for a given pair of chemicals, then I would be able to plot on a y versus x graph what my equilibrium conditions are. So for example, an alpha AB of 2 is going to give me the simplest form of this equation. So again, for example, if alpha is equal to 2, then my function is y is equal to 2x over 1 plus x. And that is going to look like a curve. So if I plot this y as a function of x, oftentimes I like to plot these in a box plot. Not a box plot, but a plot that has 4 sides filled in. And oftentimes we draw this 45-degree line in just for clarity. So this graph goes from 0 to 1 and 0 to 1. My plot, y as a function of x, is going to look something like this. So you can try that out on your calculator just for a range of x going from 0 to 1, plot the values of y that you'd get. And once again, the benefit of doing this now is for any given value of x, I could now look up and see on my plot. So if x were 0.3, for example, I just go on this green line, look up what my y coordinate is, and that would tell me what the vapor phase composition that is in equilibrium with this liquid phase composition is for any liquid phase compositions. So in the next video, I'll show you how to use one of these plots in order to solve an entire problem graphically, but I just have a couple of quick notes about relative volatility to end this video. So the first note is that if we're using alpha to graph this relative volatility plot, this y versus x plot, it must be a constant value. In other words, I can't have an alpha that is changing with respect to temperature, pressure, or composition. If that's the case, then a graph like this is not going to work because I can't plot it with a single parameter. In real life, this is very rarely the case. So many chemicals do not have a constant relative volatility. And for that reason, I think that that is why Alan Lane does not discuss alpha very much in his textbook. But I do want to make the note that even if you did have a TXY diagram and alpha was not constant for it, you could still convert the TXY diagram to the YX diagram simply by plotting y as a function of x instead of t as a function of y and as a function of x. So I'll show you what I mean there. If I'm given what a TXY diagram is, and for a non-constant alpha, I'd probably have a weirder looking TXY diagram. So maybe something that wasn't nice and symmetric. Maybe it'll look something like this. I don't know, I intentionally exaggerated it just to prove the point that you can do this. You could convert simply by taking various temperatures, and it doesn't matter what temperatures you use as long as you do the entire range of temperatures, and you could read x and y coordinates off of this plot. I drew this TXY diagram in terms of the less volatile component, so I should have drawn it. Let me try again to draw it. Let's draw something like, right, something like this. I know that it has to begin and end at the same point. So for certain values of temperature, I'd go to my TXY diagram, I'd look up what the X's and the Y's are. This is my X coordinate, and this is my Y coordinate, because this is the dew point or bubble point curve. Try to answer that to yourself. So remember that for a temperature TXY diagram, high temperature corresponds to vapor. And if I'm in the vapor region going downwards, this is going to be my dew point curve. And dew point curve is where the vapor phase composition is. All right, so I'd take this XY pair and I'd just map it over to my YX diagram. So not T on the Y-axis, but Y on the Y-axis, X on the X-axis. And I would get several points. So this is for a very low value of X, but a high value of Y. So this data point may be somewhere there. And I would keep going. So I'd plot different X's, get the corresponding Y's. So those are the first two data points. And I might find that my YX diagram would look something like this, right? This is called the Y equals X line that I'm drawing in, by the way. This is something that I commonly put into my YX plots just as a reference. So because Y and X are corresponding to YA and XA, and that is oftentimes implied such that I don't always write it. Remember, YA always has to be greater than XA for non-azeotropic mixtures. So if I have A is the more volatile component, the composition in the vapor phase is always going to be greater than that of the liquid phase. That's going to wrap up this video. As I said in the next video, I'll show you how to use this YX plot to solve the entire flash distillation problem completely graphically. So I'll see you in the next video.